All right, welcome back. This is part 2, video 2 of our review for our exponentials exam. We're going to start with the parent function. So first thing we're going to talk about is transformations from a parent function based on the equations. So let's say we have a function f of x equals 2. This would be considered the parent function with a base of 2. Now, all of these transformations, right, this is a base of 2, all of these transformations are the same whether it's base of 2 or 12, or if this was like base of 3 or base of 5. All of those are their own parent functions with different exponential bases, okay? So if we have the parent function, f of x equals 2 to the x, okay? And then we have another function, g of x equals, we'll start with 2 to the x. If we manipulate this function and transform it different ways, those are our transformations. So when I multiply by 3, okay, this type of transformation is called a stretch of 3. The technical term is actually that it's a vertical stretch of 3, but for our classes purposes, the concepts that we're looking for, we're just dealing with vertical stretches and shrinks. So this would be a vertical stretch of 3. You just need to know that it is a stretch of 3. And the reason that it is a stretch is because 3 is a numeric value that has a absolute value that's bigger than 1, okay? Right? If 3 was smaller than 1, or if we were multiplying by a factor that was between 0 and 1 is actually what I should say. Like if I multiplied by 1/3, this would no longer be called a stretch. This would be called a compression. So this is a compression of 1/3. So go ahead and write that down. This is now a compression of 1/3. Let me make this clear. If you have a negative in front and a 3, you're not going to view this as, oh, this is smaller than 1, because negative 3 is smaller than 1. You're going to be like, oh, this is a compression. That's not what we're doing. If we have a negative, as well as a numeric coefficient that multiplies in front of this, those would be considered two separate transformations. The negative would be separate from the 3. Let's just go one of those at a time. So we've already dealt with, hey, if the number is bigger than 1, that's a stretch, so stretch of 4. We've dealt with if the number is between 0 and 1, like 1/2, that's a compression of 1/2. Now let's just talk about if we have a negative in front. If we have a negative in front, this is a reflection. What that means is our parent function, which if you look at it has an asymptote at 0, okay, which was previously a growth problem, has now been flipped. I'll use blue to show the graph of the transformation. It has been flipped and reflected over this asymptote. Our reflection always takes place over the asymptote, okay? And it is not called a growth problem anymore. This is neither growth nor is it decay, okay? It is technically growing in negativity away from our asymptote, but for this class and the content in the state of Georgia, Algebra 1, this is classified not as growth and not as decay, okay? But that's what happens when we have a negative, okay? Just so you know, when we have a stretch, what that does is that starts making this function steeper, okay? So it grows at a steeper rate. So if we have a stretch of 3 and a reflection, it is going to be steeper in its negativity, okay? So I want to highlight that real quick. In fact, let's take the graphs down. If we have a negative there and a 3, we consider this as two separate transformations. The negative is our reflection. The 3 is our stretch of 3. If we had a negative as well as a fraction, we would consider this a reflection and a compression of 1/2. Okay, let's talk about our asymptote. Our asymptote is featured right there, all right? And our asymptote rises or falls based on whatever this number is. So what previously would have been a function that looked like this, a growth problem where our asymptote was at 0, has now been shifted up 4, meaning the asymptote has moved up 4, because this is the location of the asymptote, and our function has been moved up 4, okay? So shifts out here that we add are vertical shifts up or down. So that last one was a shift up 4, and that's the picture representation behind this, okay? So if we had -3, this would be a shift down 3, all right? Now, shifts that take place in the x, we actually have to do the opposite direction. And the reason for such, so let's pretend that that shift is not there. We have the function 2 to the x. I want you to imagine plugging in the value of 0 for x. 2 to the 0th gives a height of 1. So that is why our y-intercept is right there at a height of 1. Okay? Now watch what happens as I add 3. You would think that this means that it now moves to the right 3, but it does not. Okay? It actually moves to the left 3. It goes in the opposite direction. What that basically means is this point is now right there. And that actually makes sense, because if you think about it, if you plug in -3 for x, that would zero out my exponent. So you're actually asking, what value would I plug in to zero out my exponent? -3 for x zeroes out my exponent, because -3 +3 makes 0. 2 to the 0th is 1. So that point that was here has now moved 3 spaces to the left. Okay? So this is a transformation left 3. And we basically do the opposite of that sign, because we're asking ourselves, how would we zero out that exponent? Okay? So if I had, here's our 2 to the x. If I had 2 to the x -1, this would be to the right 1. Okay? So let's add all of these ideas together, and let's look at the function f of x equals -5 times 3 to the x minus 2 plus 7 power. Okay? Sorry, x minus 2 power plus 7. Sorry about that. Lots of transformations going on in here. So let's identify each one. The negative, that means it's reflected. It is below the asymptote. It is neither growth nor decay. It is reflected under it. Okay? The 5, it is a stretch of 3. Sorry, it is a stretch of 5. 3 is our base. That's our parent function. So the parent function technically would have been this. Okay? So reflection is the negative. Stretch of 5. Base of 3 is not a transformation. That's our parent function. To the right 2, because of the opposite sign there. Up 7. Those are all our transformations. Okay. If we want to talk about how would we graph this, or how would we identify the graph, first thing we would look at is our 7. And that is our asymptote. Okay, we know that this would have been a growth problem, but it is reflected and stretched. So here would be the regular reflection, here would be the stretched. And obviously, we have not actually gone into detail of how to graph these perfectly. We actually have not had you plug in values to find exact points. What we've had you do is match graphs with what it's supposed to look like. So we've done basically very vague graphing. And with a multiple choice test, it would be the main components that you would need to know out of this is identify the asymptote, the height, identify that it is flipped under, and it should be growing away from our, and it should be growing away from our asymptote, because this concept, had it not been flipped, would be a growth problem. Okay, so that is the how to graph as well. Short time left here to get this all taught. So let us look at identifying if it's growth or decay. Is it growth or decay? And in reality, all we're looking at is the base. In this case, my base is 1/2. and my base is between 0 and 1, therefore it is decay. Okay, that's all we're really looking at, as long as we have a positive coefficient there, and as long as there's a positive number there. Okay? So for example here, it does not matter that there's 1/2, -1, +2. What matters is we have a base of 3, meaning this is a growth problem. Okay? Here, this would be a growth problem, nothing to do with this, this, or this, just having to do with the fact that it's a 3 there. Okay? It would be a growth problem, but we have this negativity, which means it's neither growth nor decay because it's reflected underneath. All right? Once again, would have been decay, but we have this negativity, so it is neither decay nor growth. Here is where we get to a tricky problem. Notice, it is a negative coefficient in front of our x. What previously looks like it was growth is not really growth, because if you recall, negative exponents means this problem is really 1/3 raised to the positive exponent. We flip that base. Okay, so this is actually a decay problem. I'm going to let that sink in for a minute. I'm going to let you guys understand that and put that into your notes. I'll pause. All right, this one again, typical growth. Positive in front of here, positive right there, bigger than 1. Okay? Next one right here. All right? Bigger than 1, so it's a growth. It's barely bigger than 1, but it's bigger than 1, it's a growth problem. Right here, smaller than 1. Let me make this clear. Not every fraction is decay. For example, if I had the fraction 7/6 to the x power, clearly bigger than 1. 7/6. 7 is bigger than 6. It's bigger than 1. This would be decay. This would be growth. Keep this all in mind, guys and gals. All right, characteristics from a graph. Let me pause this real quick so I can get this set up. All right, first off, we're going to go through identifying characteristics from a graph if the graph is already drawn for you and shown to you. Let me make that clear, okay? Couple of the key ones that I want you to understand. Domain. We're going to talk about domain. Now, the nice thing for all of our exponential functions, whether they are growth, decay, or neither, no matter what they are, growth, decay, or neither. So even when it's down here, okay, our domain is going to be all real numbers. Now, if they ask us to write that in inequality notation, that's what we would do. Typically, though, I could see them wanting us to write this in interval notation. And interval notation for all real numbers looks like this. -infinity to infinity. All right? So keep that in mind. When we talk about the range, all we are looking at is our asymptote. We are saying it's either above, you know what, I'm not going to write that down, I'm just going to talk to you guys. We're basically either saying it's above the asymptote or below the asymptote. We need to know the height of the asymptote. Here, our height is 0. It's on that 0. I know I didn't draw it beautifully, but it is on that 0. Okay? It is either above that or below it. Clearly it's above it. How do we say above it? Y is greater than that. Okay? Very straightforward range for this problem. Okay? If we did not have this function, if the function was somehow flipped, okay, the range would be y is now below that height of 0. Okay? if the asymptote moves to a different height, let's say the height now of this asymptote is at a height of 3. Our function is below it. It is still y is less than, but now it would be less than this new height. Okay? All of this so far has been inequality notation. If we want interval notation, okay, we start with our lowest value, which is down at negative infinity, right? That's the lowest height, and the highest height, 3. And remember, an asymptote is a line that is always approached but never reached in one of our directions. We don't actually get to that height of 3. Okay? If it was above this, so let's say our function was above this, our low value would be positive 3. Our high value would be infinity. We would never get there either. So this covers range in both types of notations as well. So let us talk about increasing versus decreasing intervals. For all of these functions, they're either always increasing or always decreasing. So let's say we have our asymptote. Let's say the function is above that and going up. This is clearly an increasing function. Just so you know, this is also the picture of an increasing function. Either of these two are always increasing. Let me make that clear. Those are two separate functions. I just threw them on the same graph, but both of them are clearly always going up. So either of these pictures are always increasing. So when we ask you where is it decreasing, it's never decreasing. There is no region in which it's decreasing. If we ask you where is it increasing, we're probably going to ask you in interval notation, and this is how we write always, or every number. For every number, here is the domain for which it is increasing. Does that make sense? That's how we're writing that. Here's a picture of something that is decreasing always. I'll show you the bottom side also. Not the reflection of this, but a separate graph. Here, I'll just actually do a separate graph this time. Here's a separate graph. This is also something that is always decreasing. It's always going down to the right. Both of these are always decreasing. How would we write that? From negative infinity to infinity, meaning always decreasing. Okay? Now the other idea that we need to know is the y-intercept. That is always just going to be a coordinate, 0, comma something, and you actually have to count out and identify what that numeric value is. In this case, 0, comma 3, or in this case, I don't know, 0, comma 1.5. Okay? But that's just a counting concept. Another counting concept is, so one more concept that is counting would be, if we're talking about the x-intercepts. So let's say I have the asymptote below it, okay, and it crosses somewhere, and it's above it. Now we have an x-intercept, and that would be, again, the coordinate with now a height of 0. So again, just a counting concept. Just a counting concept. Let me make that clear. Just a counting concept. Boom. Very easy to do. But what does the x-intercept tell us? This helps us separate, basically, left half from the right half of our function. The reason we want to know the left half and the right half is because at this location of -1, it crosses from negative to positive. So we're basically saying for a positive region, for a negative region, 1/2 is going to be positive, 1/2 is going to be negative. How do we write which one is which? Well, this one is clearly the negative half because it's below the surface on the left-hand side. How do we write left? Well, x is less than -1. This would be inequality notation, or greater than -1 means the right half. That's inequality notation. However, we need to be comfortable with interval notation also. So there's 3 numbers that I taught you guys to be prepared for. Negative infinity, that's far left. The actual x-intercept, where it changes from negative to positive, right? Why does it change there? Because that's where it passes the 0. And then the far right. So now our left half is from negative infinity to -1. And that happens in this case to be negative because it's below the surface. And the right half from -1 to infinity, right? Because that's where it's above the surface. Let me show you if it was flipped. So if the function went down, so check it. If we had the same function and it crosses, and I'll move this over so that it goes down at -1. Once again, here's negative infinity. Here's positive infinity. We call this the left half because it's the left side of the graph once we split it in half, right? This is the right half. Okay? This side is clearly positive. This side is clearly negative. So our positive region is from negative infinity to -1. Our negative region is from -1 to positive infinity. Okay? The end behavior of a graph, if you recall, end behavior, x goes to one side, y goes to another, x goes to one side, y goes to another. And it could say y or it could say f of x. Left side, right side. That's what that means. Watch this a couple times through if you need to. The bell's about to ring, so I'm going to be cut off on my teaching. Height goes up forever on the left, right? Check this out. This problem, it goes up forever on the left. On the right side, it goes to this height of this asymptote. So I actually need to know what the height of that asymptote is. -3. That's the height that the right side will always approach. All right? All right, that's all the time that we really have for this lesson of review. The only other skills that I don't have time now to review with you guys are geometric sequences in recursive and explicit form. Now, thankfully, we spent all week doing that, so that's why I did not incorporate that in our review video. So you need to study for the test for geometric sequences, recursive and explicit rules. Go back through the practice problems we've done in detail in class the last couple days. Thankfully, we have gone over that a lot. So I hope this helps.